Okay, all right. So, Fourier transform, we will look at the formulas again. This will be important for our all the lectures in fact. So, it is defined, we are in field theory we will use infinite box, okay, unlike finite time series, or in turbulence we have finite box, but we will use box to infinite in d dimensions. Okay. So, d could be 1, 2, 3 or 4 as well, or even fraction. So, for Fourier series, Fourier transform, one condition is that f x must be square integrable, okay, that is a condition. So, that means the integral of f x squared, mod f x squared, f x can be complex, okay, like wave function in quantum mechanics is complex. So, mod f x squared integral is finite, okay. So, this is a condition. So, please make sure that this condition is valid. Okay. Sometimes we let go, like Fourier transform of a unit, constant, we say delta function, that is not square integrable, but still in physics we let go of few things, okay. This is sometimes we violate it, but strictly speaking mathematicians would say that we should have this condition. Now, the definition is we are going to use for this course, f x is a function in real space, x is a real space coordinate x, y, z, and k is the wave number k x, k y, k z. So, I represent the Fourier transform of f x as f hat k, we put a hat, okay. Right now this means just a complex number, but later on we will, this hat will also be used for operators, okay, but right now we just think that that is a complex number. So, we can go from Fourier space f hat k to real space, the function can be complex in real space by multiplying this by exponential e I k x, a k dot x is a dot product, and I integrate with this dk divided by 2 pi to the power d, okay. This 2 pi to the power d is because of normalization, okay, and so this is the integral. So, so now you will always find this kind of combination in quantum field theory, okay. In 1D it is going to be just dk by 2 pi, okay. So, you basically blindly put dk by 2 power d. In Fourier, so this is called inverse transform, you go from Fourier space to real space, inverse transform. Now, I can go from real space f x to Fourier space. So, I just have to do integral dx e power exponential minus I k x, please note the minus sign. So, that is the notation I will follow for f hat k to f x plus sign and f x to f hat k minus sign, okay. That is the notation we will follow in this course. There is no 2 pi division here, okay. Now, this normalization is, if I in fact f hat k, this definition, if I do dk by 2 pi power d, this should give me, if I in fact integrate this, I should get 1, no sorry, if I do this I should get back f x, okay. So, you can do it, you can check it yourself that this is consistent, we can invert it. So, you play around with this is standard stuff in quantum mechanics, you might have done it, or mathematical physics, this standard definition. We will follow this definition in this course. Now, this is for real space dimension to Fourier space. Now, sometimes we will also need to do the Fourier transform or time series as function of time, f of t. So, time and frequency, so this is also Fourier transform, So, you have time series, we can do the Fourier transform, that will give you frequency. So, if I have a time series f t, I integrate from 0 to t, okay. So, time series starts from t equal to 0. Sometimes people start with minus infinity to infinity dt, but then we assume that f t is 0. So, if you see minus infinity to infinity for t, this t, then my function is 0 in this regime, and then it may start like that, okay, f of t. So, for this part the sign is flipped. So, this is a plus sign here and minus sign here. So, when I go from Fourier f hat omega to f t, I put a minus sign. If you recall, for my real space stuff, I had put I k dot x for going from Fourier to real. It is a plus sign here, but here I put a minus sign. The reason is quite obvious, that imagine a wave going in the x direction like this. So, what is this wave written as? We normally write, you might know, that e to the power I k x minus omega t. Okay. So, k is positive. So, wave propagating along x direction, k is positive, no, this is a positive momentum. So, k is positive and omega is also positive. That is why x and t both increase with time. Well, x is increased with time and time of course increases. Okay. So, the wave going in the forward in the right direction is given by that. So, there is a plus sign for I k x, this one, but minus sign for omega t. Okay. So, please remember this, there is a minus sign here, and now inverse transform f t to f at omega, I have to put a plus sign. Okay. So, this is when we just deal with time series. There are times we just deal with time series, but often we deal with both space and time, right. Wave function is function of space as well as time. Then I have to transform from f x t, f is function of position and time, to f at k and omega. Okay. Now, this function is e to the power I k dot x minus I omega t. Okay. So, as I said, for the waves. So, imagine that we have some function which is function of x and t. I am Fourier transform is a function of lot of waves moving in time. So, this is the amplitude f at k. So, for a wave of wavelength k, and also frequency is also, I mean, you also transform, rather decompose in frequency space. Right. So, we will see some examples in a while. So, this is both space and time. Okay. So, I just combined last two slides and we get here. Now, we can get, so this is from going from Fourier with k and omega to real and time, but we can do the inverse. I can get from f x t, I mean my function which is in real space is a function of time, I can go to f at k omega, and the sign is of course we need to flip it, this becomes minus and this becomes plus. Okay. So, we need these definitions, so I thought I will put it here. Okay. So, this is about it. I can take some questions if you have any. All right. So, this fine.